Hey physicists, it's Mr. Gopal. Super excited today for this lesson. I'm back in school, as you can see. So excited to hopefully just continue this trend and get everybody back here. And I'm especially excited about this lesson as we're coming back because I happen to teach at a music school. And so I wanted to get into some of the physics behind music, behind sound specifically. Today we're going to talk about the Doppler effect. Now, I think the Doppler effect is a really great lesson to use to teach physics because we all kind of encountered this at some point in our lives. If we're walking down the street and we have a car go by us, say an ambulance or a police car, one that has a siren going. All right, and usually what we've experienced is that there's this kind of weird pitch shift, but perhaps we haven't necessarily specifically analyzed that pitch shift. And that's something that I want to do today. I'm just going to kick off with this video and then talk a little bit about what seems to be going on. So physics is a class that's best experienced through experiments. And so I hope this one will help us kind of shed some light on this phenomenon. All right. So what you probably noticed there, or at least what I noticed, is that when the trumpeter was in the car, when we were watching from the vantage point of being inside the car, nothing happened to the pitch. And think about it. We're passengers in the car. We're traveling with the sound. All right. So our system, you could say, we talk about systems very often in physics, meaning like whatever kind of group of objects in relation to each other we are analyzing. Our system would be the car, the passengers inside it, and the trumpet. And of course, we're all traveling together. Therefore, there's no change in pitch. However, if we are observers, bystanders on the side of the road, we see that the pitch seems to go down. It's like, so two things happened, right? Number one, there was a slide down to a lower pitch, and then that lower pitch continued consistently after some moment. That slide seemed to happen as we were kind of parallel with the car, or you could say that the car was like directly in front of us as it passed by us. Okay. So as it passed by us, that particular pitch changed. Before it passed by us and after it passed by us, the pitch was fixed, but before it passed by us, the pitch was higher than after it passed by us. And this is the Doppler effect. So what could be going on? I'm going to show you an illustration that I really like that kind of lays this out very, very easily, or in a way that's easy to understand. So if we take a look here at this particular picture, okay, we can see the ambulance. All right, so let's say there's an ambulance, the siren's going off. All right, we've got two bystanders. This is two-dimensional, but picture these two people are on the side of the road, and obviously the ambulance is driving down the road. Okay, and so as the ambulance approaches somebody, since it is in motion, okay, since it's in motion, the pitch of the siren as it goes off, or I guess you could say the siren going off is creating sound waves that are compressing against each other. Now, when they're compressing against each other, picture each one of those circles as a wave, all right? The waves are closer together, which means they are more frequent, okay? One thing we're going to talk about, I'm going to have multiple videos on sound and waves in general. We're always going to be talking about a handful of different aspects of waves. And one of those aspects is frequency, and frequency means just how many oscillations of a wave, right? You can see that there's this kind of like wave-like form over here, it is, we would describe that waveform as oscillating, okay, meaning to go back up and down in a repeated pattern, okay? The amount of times it oscillates per second is a measurement that we classify as frequency, and we measure it in hertz, okay, Hertz, okay? And as you can see, if an object is in motion and it's giving off sound, then the sound waves are compressing against each other, coming closer together because the guy's giving off, or sorry, the ambulance is giving off new sound waves as it moves forward. On the other hand, as it moves away from somebody, right, we've got this guy on the left-hand side. As it moves away from this person on the left-hand side, those sound waves are becoming farther apart. And so part of the takeaway from all of this is that frequency is related to the pitch of the sound. By the pitch, I mean the note that you hear, like whether it's an A or a D or a G and so on and so forth. You can say the frequency of a sound wave, this sound wave frequency equals pitch, okay? We will continue to discuss other aspects of a sound wave. Okay, so there's also amplitude, which is like kind of how vertically large each sound wave is. And there's also, you could say wavelength, all right? And you can see that there is an inverse relationship between wavelength and frequency right here. In other words, I circled the high frequency waveform in blue. I'm circling the low frequency waveform in orange. And we can see with the low frequency, the length of one wave is from here all the way over to here. That is the length of one kind of like one kind of piece of the pattern before the pattern repeats itself is that long. On the other hand, over here, one kind of piece, I'm going to do it in green so it pops a little bit. One piece here is much shorter. I'm actually going to close by going over these on a whiteboard, just because I think that taking a look at this on a much bigger scale is necessary. So we had that idea of compression and expansion of waves in a moving object, okay? And so with sound, the way that that change in frequency, meaning how many oscillations of that waveform per second there are, the manifestation of that change in frequency, again, is a change in the pitch. And that's when we get farther away, the pitch gets lower because the wavelength is farther apart, or it's bigger. And the pitch gets higher if something giving off sound is approaching us, because the waves are closer compressed together, okay? And so if I were to make an XY axis here, I'm going to make two waveforms and just analyze this idea that wavelength and frequency are inversely related. Okay, so let's say I have a form like this. Okay, put arrows to show that it keeps going. We could say that from here to here, do it in green. That is one wavelength, all right? So change the color so it pops. I'm gonna put it actually up here. Green arrows indicate one wavelength. Okay, and now I'm going to make a one with a smaller wavelength, and we're going to see that it's going to be more frequent. So I'm going to do that one in, let me see, do that one in blue. And so now, oops, I'm going to choose blue. Okay, and obviously it's a drawing, so it's a little bit off. Like all of my peaks and valleys are not exactly lined up, etc. But the point remains that if I make arrows, this time in orange, that depict the length of one wave. So I'm going to put a text box down here. The orange arrows one wave for blue sound wave. Okay, and so we can see that the length of one wave is much shorter. However, we can see that it's oscillating more frequently in the same span of time. This guy goes up and down twice. The other one goes up and down once. So it's roughly double the frequency and half the wavelength, okay? So my point stands, and I'm gonna write it to the side. Wavelength and frequency vary inversely. Now, I just want to talk really quickly about how this manifests. With sound, increases in frequency correspond to increases in pitch. Okay, now with light, which we're going to talk about in more and more often, I got cut out of there, select, there we go. With light, increases in frequency correspond to changes in color. Okay, so you may remember, and if you don't, this is on the reference table. This is a nice segue into some of the videos on light that I'm going to be putting up. But you may remember that there is a band for the frequencies of different colors. Okay, and so blue has the highest, blue or indigo has the highest frequency. If we go all the way to the lowest frequency, longest wavelength, it would be red. And so this goes back to the idea of the universe expanding. Okay, if things are moving farther apart and we see stars and planets and other galaxies moving farther away from us, there is a red shift or a red hue to them. If they were moving towards us, there would be a blue shift because the frequencies would be compressing, right? Since the frequencies, the waveforms would be compressing. Since the waveforms are getting farther and farther apart, we have a red shift, which is how we know the universe is expanding. And you could say that that is a Doppler effect in the whole universe. So this is pretty cool. This is really powerful stuff. We heard it with the sound. We're going to examine a little bit more with it with light. But again, just to go over it again, the Doppler effect is this key to cracking very important phenomena about the way that waveforms work. Okay, we can see it here. As an object that is giving off sound comes towards you, the sound waves are compressing closer and closer together, which means that the frequency is increasing, and we hear that as a higher pitch. Okay. Then, as the object giving off sound passes by us, there is a shift downwards, because as it goes away from us, those sound waves are traveling with the object, so they're getting farther and farther apart as they reach us. Hence the lowering of pitch. I hope this has been helpful for you. Take care, and I will talk to you soon.